Welcome back, ladies and gentlemen, to AP Chemistry with Mr. Kenton. We got an exciting time for us today. We're jumping into electron configuration and atomic structure. And in order for us to begin, just so you know, this is coming from Chapter 6 in our Brown LMA textbook. And we're going to be kind of taking a little bit of a detour while we're going through this, but we're going to hit some things that are fundamental to our understanding of the electron. And in order to do that, we got to look at waves, we have to look at light, we have to look at energy. So that's going to be where we're moving now, but we're moving into, within Unit 1, as we've been going through here, we're now into topic 1.5, which is atomic structure and electron configuration. Now you can see this is coming from Chapter 6. There are quite a few questions that correspond to this from our textbook. So obviously, as you go through this and as you watch this, make sure you go and answer those questions as you get that information. And, let's just dive right in. This is going to be fun. So when we think about atomic structure and electron configuration, we all have kind of this idea of what the atom looks like. And, maybe it's the picture of like Jimmy Neutron and how the atom looks and things like that. But it's been a lot more structured. And really, the model of the atom has changed a lot since it was first proposed. Okay, and so just having that as a backdrop, it's really neat just kind of understanding how scientists, as they gather more and better and new information, they're able to take that in and use it to make modifications to models that they have, right? And so where we're at now is what best matches up with the information that we have. But right now, what we're going to do is we're going to take a look at how scientists and chemists were able to get to and develop the quantum mechanical model. And it wasn't always, oh, well, we think it's the quantum mechanical model. There were some things that scientists were confronted with and had to really wrestle with to better understand this. And it's going to start with our understanding of light and how light and electrons really have an interesting relationship. So let's go ahead and take a look at this. So you probably remember that a wave can look something like this. This is a transverse wave for those of you who remember your physics. There's also compressional waves, but this is a transverse wave. And, for us, waves are important because they help us understand the electronic structure of atoms. Because in some senses, what we know is that electrons are a particle, but what we also know is that electrons can behave like waves. And so to understand electronic structure of atoms or electron configuration, we need to understand the nature of electromagnetic radiation. And remember, that term electromagnetic radiation is just a fancy way of saying we're dealing with light. Okay, so electromagnetic radiation and light can be used interchangeably here. So let's dive in. Now, the distance between, obviously on this wave, we can see the distance between corresponding points on adjacent waves is the wavelength, right? So you've got from the crest to crest in this particular case, those two high points. You could also go from here to here. That could be a wavelength, going from trough to trough. And then you've also got the amplitude, the height of the wave as it moves from the equilibrium position, that black line that's going through the middle, to the peak of your wave, right? Now, these are just very basic identification principles of what's your wave, of parts of a wave, right? Now, also, when you look at waves, it's important to think about, so we had wavelength, we had the amplitude on the previous slide. We can also think about frequency, right? So how many waves are passing by a given point in a given time period. And so like when we look at the two waves that are listed there, I think it's pretty evident that the wave that's on top has a greater frequency. There's more wavelengths that are present in that top wave than in the bottom one. And so we would say that that top wave has a greater frequency. And then you notice that frequency is given that Greek letter, the mu, right? Or excuse me, yeah, it's mu, I think. It's either mu or nu, I don't remember. I'm not Greek, so I don't use the Greek alphabet all that often. Right? And so the thing is, for waves, specifically light waves, they travel at the same velocity. And so the longer the wavelength, the smaller the frequency is going to be, right? So the bottom wave is longer, and so it has a smaller frequency. The wave up at the top has a shorter wavelength, and so it has a higher frequency, right? So it shows us that inverse relationship between wavelength and frequency. Now, that leads us into electromagnetic radiation, because electromagnetic radiation, or light, or radiant energy, it's on this spectrum, and that's where you've got gamma rays, you've got X-rays, you've got ultraviolet light, you've got the very small portion that's visible to us, you've got infrared light, microwaves, and radio waves. And the unique thing about all of those forms of light is that they all travel at the same speed, right? And so they all travel at the speed of 3.00 times 10 to the 8th meters per second. Now, in order to account for that, we talk about speed of light and how wavelength and frequency mix together. That means that our waves that have a short wavelength, like our gamma rays, notice that their wavelength is starting at 10 to the negative 11th meters. They account for that, they make up for that by having a very large frequency. Notice that the gamma ray in a second, 10 to the 20th gamma rays will pass by a given point in a second. Whereas if you move down to something like a microwave, that's in the range of 10 to the negative third to 10 to the negative first, but then it has a frequency of something like 10 to the 11th, 10 to the 9th, right? And so there's obviously that trade-off. But the neat thing is, whether it's a gamma ray or a radio wave, it doesn't matter. They all travel at the same speed, 3 times 10 to the 8th meters per second. And so we get this relationship that the speed of light is going to be equal to the wavelength times the frequency. So C equals lambda times nu, where lambda is the wavelength and nu is the frequency. Now, it's important here, your wavelength in this equation is going to be measured in meters, and your frequency is going to be measured in inverse seconds. So just keep that in mind in terms of your units. You might also see hertz, but hertz and inverse seconds are interchangeable for the frequency. All right. Now that we've introduced electromagnetic radiation and light, you might wonder, okay, how does this relate to the electron and atomic structure? And it's important because as scientists were developing their model for the atom, as they were beginning to look at light, it was giving them some insight, but there were some things that they didn't really understand that, as we go forward, are going to lead us into this idea that electrons can behave like both waves and particles. And one thing that kind of comes up is that the wave nature of light, so when we talk about light, we think of it as a wave, right? We don't really think of light being something that's got particles that make it up. We don't think of it as something like, it's waves, right? We wouldn't necessarily say that a wave has mass. But the wave nature of light didn't explain properly how an object can glow when its temperature was increased, right? You take a look at the image that's over to the left. They've got some sort of metal that they've heated up quite a high temperature. And we know that that's hot because that liquid is glowing, right? I mean, it's, you got that white glow, you got the orange glow, you kind of got the reddish glow, and you're like, yeah, that's really hot. And so the idea that light is a wave is kind of our foundational principle, but the wave nature of light doesn't account for the reason why objects glow when their temperature goes up. Okay, and so that was a shortfall of understanding light from the perspective of light just being a wave. And so then we got to think about, okay, so how do we deal with that kind of anomaly or problem? And so that leads us to Max Planck. And what he was able to look at is he explained kind of this idea that a particle, it would assume that energy comes in packets called quanta, right? And so when we talk about an object, whether we're heating it, whether it's giving off light or giving off energy, it's going to give it off in these quanta, these packets, these specific amounts, right? And again, he used this as an assumption. He didn't know this to be true, but that's kind of something that he wanted to test and how he wanted to look at to see if that was actually a valid explanation for this phenomenon. So, and again, those small packets are called quanta, and you think about it, a quanta of energy, a specific amount of energy that's being released. Forgive me, my nose is running. Right? And so, Max Planck looks at this idea of energy being given off in quanta, specific amounts, and come to find out that's true. And so Max Planck creates an idea, creates Planck's equation, which we're going to see here very shortly. And the cool thing about scientists is that once a scientist makes a discovery, other scientists can then use those kind of conclusions that get drawn to help explain other phenomena. And so Albert Einstein used Planck's idea to explain what's called the photoelectric effect. Now, the photoelectric effect has to deal with the idea that you can shine light on a metal, and when you do that, it's going to cause electrons to leave the surface of the metal. That's the photoelectric effect. And you can see kind of the setup that's over to the right in that picture. They've got a piece of metal, and then what they have is, they're showing that they're shining light on it, and they're showing that the electrons would be given off. Now, obviously, if you just shine it on a metal, you're not going to be able to capture the electrons. So what he did is you got a voltage source, you got a battery, you got a current indicator, so like a voltmeter, and you've got a metal that's in a sealed container, and you place a positive terminal in there. All right, so then you shine light through that, it hits the surface of the metal, and then the electrons become attracted to the positive terminal, which then leads to the voltage source and the current indicator, right? And so Einstein kind of used that idea to be able to identify and explain why metals, when shined with a specific energy of light, would give off electrons. Okay, and so from that, Planck and Einstein both concluded that energy is proportional to the frequency of the light that's used to cause the electrons to be given off. So E equals H, which is Planck's constant, times nu, the frequency of the light that you're using. Now here H is Planck's constant, and it's got a value of 6.626 times 10 to the negative 34th joule seconds. Okay, and notice that when you take Planck's constant and multiply it by the frequency, you would get a unit for energy, joules, which makes sense. Okay, so there's the photoelectric effect, and again, the wave nature of light, well, important here, again, didn't fully capture why light was causing an electron to be given off in the first place, right? You've got something that's not a particle causing a particle to be given off. So what's really going on here? So it's kind of interesting, food for thought. All right, so kind of what we've looked at this point, we've seen that all radiant energy, all electromagnetic light or radiation travels at the same speed, so we can use the expression C equals lambda times nu, wavelength times frequency, to calculate its speed. And then we just saw from the photoelectric effect in Einstein and Planck that the energy of light, or energy of something, is equal to h times the frequency. So Planck's constant times the frequency. So if we know the wavelength of light, then we can calculate the energy in a photon or packet of that light, so that quantum, right? And so this is taking that idea that light is now not necessarily just a wave, but it's made up of tiny particles of light. And so again, a photon is just that packet of light. Think of it as your quanta of light. And so if you know the wavelength of that light, you can calculate the energy of it, right? And so as long as you know the wavelength, like if you look at the laser pointers that are there, if you know the specific wavelengths, you could calculate how much energy does, let's say that one of those green lines is giving off. Okay. And again, this was groundbreaking. This is not something that was known, and this was helping frame our understanding of what light and the electron behavior was going to be. Okay. Now, something else that kind of bothered scientists during this time period is this idea that there were certain wavelengths of light that atoms were giving off. And this was known as an emission spectra, right? So an emission spectra is observed from energy emitted by atoms and molecules. So for example, you probably remember that we had those gas discharge tubes in class, and you pass an electrical current through it, and it causes the gas to be excited, the electrons to move, and it gives off a specific wavelength of light. Well, that wasn't something that was very well understood at the time, and so scientists were trying to figure out what is going on here. Now, the thing is, when atoms and molecules, or specifically like an element, when you pass that electrical current through it, the reality is that the atoms and molecules, they don't give off a continuous spectrum, right? And so what I mean by that is that they don't give off all of the different colors of light that are visible. They only give off specific portions of that spectrum, right? Like you think about white light or something that you have a prism with, you can pass the white light through a prism, and then it's going to project, and you're able to get the different colors of light. But with our elements and our molecules, they would only give off specific colors of light. Like maybe they would give off red, yellow, and green, but they wouldn't give off any blue, orange, and purple, right? And so this was fascinating to chemists because they were saying, okay, so instead of it giving off a continuous spectrum, it's giving off a specific spectrum, a specific amount of light. So is there a connection between these specific wavelengths of light given off and energy that we need to think about? Right? And so that's what your elements, so for example, like they show you sodium and hydrogen there, a line spectrum shows you only discrete wavelengths that are observed. So like for sodium, you've got those lines that look like yellow lines at, 590? And then with hydrogen, you've got some lines that are at 410, 435, 487, and then like 655, something like that. So you've got these specific wavelengths that are being observed. And so then the question is, okay, what do these specific wavelengths correspond to? So that was the next question that scientists were trying and chemists were trying to kind of understand here. So then we move into Niels Bohr, and I mean obviously we probably remember him from the Bohr model of the atom, where you have the orbitals are the energy diagrams where you've got the rings, and the rings go around the nucleus. And so not only did Bohr work on kind of that planetary model of the atom, but he also studied light. And so Bohr adopted Planck's assumption that light was given off in small quantas, in those photon packets that had a specific energy. And so using that idea and the ideas of Planck and Einstein, he was able to kind of make the following conclusions. He said, the first thing is electrons in an atom can only occupy certain orbits. And he called those orbits energies. And so that's kind of, you think about like your first, second, third energy level, or the first, second, third ring going around your atom, right? And so electrons can only exist in those orbits. They're not going to exist anywhere in between, but they're going to be in one of those orbits, one of those corresponding energies, right? The second thing that Bohr proposed is that those electrons are permitted in those orbits that have specific allowed energies, and these energies will not be radiated from the atom. Now that sounds kind of crazy, but again, all he's really saying is that the electrons have to have a specific energy, and they're going to be in a specific place within the atom. That's what that point's trying to communicate to us. And then the third thing that he proposed is that this idea that energy is only absorbed or emitted in such a way as to move an electron from one allowed energy state to another as defined by that energy equation that Planck and Einstein proposed. Now, if you're looking at this diagram that's over here, you could think of it as the number 1, 2, 3, 4, 5, and 6. Those are the energy levels. And so what Bohr is proposing is that an electron could move from 1 to 2. It could go from 2 to 3, or maybe it could go to 2 to 4, or it could go from 4 to 3, or 6 to 4, or 6 to 3, 6 to 2. But it's not going to move anywhere in between. There's not going to be an electron that's in energy 1, and then it goes somewhere in between 1 and 2 and just kind of hanging out. And so, it's going to be emitted as it goes from, let's say, a high number to a low number. So like going from 6 to 2, it would emit energy. But if it were to go from something like 1 to 2, it would be absorbing energy, allowing it to move into that state. And again, you could calculate that energy using this relationship of E equals h times nu. Okay, now it gets a little bit more complicated than that. The energy absorbed or emitted from the process of electron promotion or demotion can be calculated by the following equation. Now remember, this equation right here, the Rydberg equation, is not on your reference sheet for the AP exam. So you either need to commit it to memory or, just get comfortable with it, or just know the values of things and how to use it. But it states that the change in energy is going to be equal to negative RH, where RH is the Rydberg constant, times 1 over n sub f squared minus 1 over n sub I squared, where n sub f, that's going to be the final energy level, so where the electron ends up at the end, and n sub I is going to be the initial energy level that the electron was found in, right? All right, so with that, that's going to end kind of this video. It helps us get through kind of the development of why light was such an important factor in our understanding of the electron. So take a break. Thanks for joining me, and I look forward to sharing with you some more stuff on the model of the atom and electron configuration.